very happy to have Ian Moult from Yale University to come be our speaker. Let me tell you a little bit about his kind of path through academia before kind of introducing his physics program. So Ian graduated from University of British Columbia for his undergrad before completing a PhD at MIT. He did a postdoctoral stint at UC Berkeley and Stanford before joining the faculty at Yale. So Ian works, I would say, kind of centrally around kind of collider physics and like the dynamics of particles interacting at high energies. But I would say kind of with like a real imperative to be connected to things that experimentalists measure and care about, which I think we all appreciate. He's worked, kind of his earlier work, I would say, is in something which is more related to what's called jet physics, which has to do with how particles kind of spray and explode into these kind of collimated beams of energy. At collider physics, it's a topic which is kind of nitty-gritty, but crucial to actually extract information about QCD from colliders, to actually make contact with theory. More recently, he's been really kind of the main instigator for a new program, I would say, or at least a renewed program on what are called energy colliders, which has had some lineage in particle physics and collider physics in the past, but has kind of reconstituted many ideas from very disparate fields in an interesting way. So the work, I would say, is kind of at this intersection between particle physics, kind of experimentally minded collider physics, and even string theory. And as he'll tell us, there are these ideas from kind of very formal quantum field theory that at one point were extremely abstract, pertaining to toy models and anti-de Sitter space and kind of non-realistic versions of the world, but which Ian and his collaborators have kind of very beautifully and beautifully kind of brought to the fore for really experimentally relevant physics that we care about at, say, CMS or Atlas. And I think that's a real testament to like bringing formal ideas to what really matters for what we observe. For as many contributions to the field of collider physics and QCD, he's won many awards, including the Early Career Scientist Prize in Particle Physics, the Cheung Award for Early Career Research in Quantum Chromodynamics, Early Career Fellowship, and an Alfred P. Sloan Fellowship. Without further ado, please join me in welcoming Ian for his talk.
Okay, so thank you very much for the very kind introduction. And thanks for the invitation to speak. So it's always a pleasure to visit Caltech, and I've been having a lot of fun talking with everyone today. So today what I want to tell you about is a bit of a program that we've now been working on for a few years of trying to connect, as Cliff said, certain ideas that originally originated in more formal theory, so something which goes under the name of energy flow operators or energy correlators, which I'll introduce, with and trying to use these to actually understand the standard model of particle physics in real-world collider physics, such as this kind of collision shown here. And so this has ended up being quite a long and difficult path. And it's been extremely rewarding because we've got to interact with both some kind of real formal theorists on the formal theory side, and also with actual real experimental data and with experimentalists actually doing the analyses to try and actually bring these ideas from the formal theory world to actually being able to implement them in real modern collider physics experiments. And so what I want to tell you about today is some of the kind of exciting pieces along the road, both on the formal theory side as well as on the experimental side, and then try and convince you that these are actually, or the kind of combination of these modern formal theory ideas with the modern amazing colliders at the LHC give us kind of really new ways of understanding the standard model of particle physics at colliders. Okay, so let's get started. So what this talk is going to be focused on is trying to understand these extremely complicated collisions which one gets at high energy modern colliders. And so in this particular collision shown here, we have two protons which collided at 13 TeV at the LHC at CERN, and they produce these amazing kind of sprays of particles carrying energy out into all different directions, which are observed by this experimentalist off at infinity. And so the reason why these extremely complicated and messy looking experiments are actually very interesting to both theorists and experimentalists is because these kind of patterns in the macroscopic energy fluxes, so for example encoded in this 3-point correlation which I've drawn schematically here, encode for us the microscopic details of the interactions of the standard model which happen at very short distance scales, as well as of any possible beyond the standard model of physics. And so to be able to understand the microscopic details of the standard model and really kind of probe it and push it to its limits, we really need to be able to understand how to decode these patterns in energy flux and relate them to the underlying microscopic theory which produced them. And so this puts a lot of pressure on both theory and experiment to actually be able to do this in a practical way. And so I should also say that this goes beyond just kind of a theorist kind of hypothetical picture, but this is actually how we've learned a lot of what we know about the standard model of particle physics over the last 50 years. And so in the kind of spirit of history, it's particularly fun to be able to give this talk today. So I enjoy talking about energy correlators anytime, but today, or more precisely yesterday, actually marks the 50th anniversary of the discovery of these so-called jets, which Cliff mentioned, which are just these sprays of particles which you saw coming out in these pictures. And so in these very early studies, 50 years ago, these were kind of very small jets. So they had an energy of around a few GeV, so let's say 5 GeV. And so they're essentially scaled down by a factor of 1,000 compared to what we see at the LHC today. And so if you look at these kind of baby jets shown here, you can see that these are a very far cry from the amazingly complicated jets that we see in modern experiments. But these were kind of really the start of a very long, so far 50-year journey to trying to systematically understand these objects, and in particular the correlations in energy flux in the theory of quantum chromodynamics, both experimentally and theoretically. And so this really started off with kind of very elementary studies in these, just studying the kind of correlations between particles and jets in these very early experiments at very low energies. And what I wanted to tell you about today is how this has really transformed into a kind of precision science where we can really understand these correlations at, let's say, the percent level in these very complicated LHC collisions, and really use these to probe the standard model of particle physics in very interesting ways. But before getting into that, I just want to back up a little bit about why, as a theorist, we like these collider physics experiments, what they're trying to do, and what the underlying theory which produces these complicated jet structures is. Okay, so the reason why we like colliders is that they allow us to probe physics at the shortest possible distance scales. And so one of the very nice things about our modern theories of physics, in particular gravity plus the standard model, which is just the electroweak and strong forces, is that they really allow us to describe physics over an extremely broad range of scales. And so this goes from all the way at the kind of scale of galaxies, all the way at the scale of galaxies, down to the smallest possible scales in these particle collider experiments. But of course, depending on which of these scales you're looking at, different physics can dominate, or physics from these different theories can dominate what you're interested in. And so of course, at the very largest scale, you're dominated by gravity. At intermediate scales, let's say at the scale of kind of humans, you're dominated by electromagnetism. Whereas in particle colliders, you're really dominated by the forces of the standard model, namely the electroweak force and the strong force. And so of those two, from their names, you can judge that it's really the strong force which is responsible for the kind of dominant behavior in these colliders, and it's the strong force which gives us these extremely complicated pictures which I've been showing you of these collisions happening at colliders. And so the strong nuclear force is also called quantum chromodynamics. And so this, or quantum chromodynamics, is a quantum field theory which was also introduced actually just over 50 years ago now. And so it's a Yang-Mills theory which describes the interactions of quarks and gluons. And so although this theory is both deceptively simple, so it has this very nice clean Lagrangian shown here, and it's been around for over 50 years, it actually still remains a very rich theory at the forefront of current research. And so one of the reasons why QCD remains so important, so there's kind of two reasons. So one is just it's very important in our everyday life, and you need it to be able to describe these collider physics experiments. But it's also very conceptually interesting because it has a lot of very complicated emergent behaviors at different energies. And so the famous property of QCD, which makes it so complicated to understand, is that its structure depends very strongly on the scale at which you look at it. And so famously in the UV, this theory of QCD behaves as nearly free quarks and gluons. But in the IR, it confines into the hadrons which make up your kind of day-to-day life. And so it's really this interplay of the change of degrees of freedom from the UV to the IR, which leads to these very complicated behavior at collider physics and makes it a very difficult theory to understand. And so in particular, this is what leads to these jets, or is the kind of schematic picture shown here, because when you collide particles at high energies, you start off by producing these nearly free quarks and gluons, and so things really behave as the interactions of quarks and gluons. But as they kind of evolve to the infrared, which is what you observe in your detectors, they transform in a complicated way into the hadrons which you ultimately observe. And so this is what gives rise to this jet structure and these very complicated pictures of collisions which I've been showing you. And so this makes an extremely rich theory which is very difficult to understand. And so for me, this is why these kind of particle colliders provide one of the most spectacular examples of having a very simple underlying theory, but it really produces remarkably complicated data sets. And so to be able to try and understand or learn something about, for example, the interactions of these quarks and gluons at the microscopic level, we really need to be able to decode these very complicated patterns of energy flux generated by this kind of flow from the UV to the IR. And much like in cosmology, what we would like to be able to do is to infer the kind of microscopic or early time physics from observing these patterns in the asymptotic or late time energy flux. And so this is kind of the ultimate goal of the collider physics program. But even kind of early on, you don't have to start with doing something as complicated as really looking at kind of correlation functions. So in very early simple experiments, you can actually just do things kind of by eye, by looking at pictures of what comes out of the experiments. And so this was actually enough to be able to discover the gluon. And so you don't have to do anything very complicated. Instead, you can literally look at the pictures of the energy flow which comes out of your experiment. And so in the simplest possible collision of, for example, an electron and a positron, what happens in terms of a Feynman diagram is at the microscopic level, you produce a quark and an antiquark which come out back to back. So what you actually see in your experiment is these two jets which represent the kind of kinematics of these underlying two quarks. And so you can really kind of tell, and if you measure the angular distribution, it's really that of the underlying microscopic quarks. And so this kind of illustrates why these jets are a very central role in colliders, because they're essentially proxies for the interactions of the underlying microscopic quarks and gluons. And so if you then work to higher orders in your Feynman diagram expansion, you'll get a diagram which shows like this, where you produce a gluon coming off of one of your quarks. And so the way that this manifests in your experiment is you really just see a kind of what is called a three-jet or Mercedes-Benz event, where you just get three of these sprays coming out. And so again, at this level, you don't need to do anything sophisticated to be able to disentangle this. You really just kind of look at the different pictures, and one time you'll see one that has this extra event. And so there's this famous picture of Salan Wu pointing at the original picture, and I think you literally flip through, and I think this is like the 27th event or something, where you just saw one that looked completely different. So you really didn't need much sophistication, but you're really using this kind of picture of just looking at the structure of the energy flow patterns to relate it to the underlying microscopic degrees of freedom. So as we move to the LHC, we kind of really scale this picture up tremendously. So as I said, essentially by a factor of 1,000. And so we both get pictures which look almost identical. So if you look back, this looks almost the same as this. It's just this was kind of 3 or 4 GeV each, whereas this is, let's say, 3 TeV each. So you get these magnificent dijet events at very high energies, and you also get extremely complicated events, so not just with 3 jets, but with 4, 5, 6, essentially any number that you want. And so this really provides an extremely rich data set for exploring the dynamics of QCD in completely new energy ranges, and also really in testing the higher nonlinearities in the theory. And so being able to just obtain a precise or even any description of these extremely complicated events has really been a huge driver of theory developments in quantum field theory. And so people like Cliff have come up with amazingly fancy techniques to even be able to begin to start to try and understand these extremely high multiplicity collisions. And this has really enabled us to even begin thinking about the possibility of actually describing these very complicated events from first principles quantum field theory. But it's not just the increase in energy, which is extremely interesting about the LHC. So one of the other very new things which happened for the first time at the Large Hadron Collider at these higher energies is that the LHC is the first collider where electroweak scale particles, so particles like the Higgs or W or Z bosons, or even the top quark, are sufficiently energetic that they appear very Lorentz boosted inside your detector, and they decay also into just kind of individual jets. And so this is illustrated here for a top quark, which decays into kind of 3 quarks, which you can see as these kind of 3 energy imprints here. Oops. Or a Higgs, which decays, for example, into a B and an anti-B and leads to these 2-prong jets here. And so this really brought the study of these jets to kind of the forefront, because essentially all the different particles of the standard model are in some way imprinted into different patterns of the energy flow within these jets. And so in particular, all the dynamics of the physics at the electroweak scale is ultimately imprinted into these energy flows of jets coming off to infinity. And so if you want to be able to, for example, identify that you have a top quark or a Higgs boson, you really need to understand the structure of this energy flow within jets. And so this is something which goes under the name of jet substructure. And this is something which is introduced for the first time at the Large Hadron Collider. And what it really tries to do is to use these patterns in energy flux to provide qualitatively new ways to study physics at the LHC. So if you really understand the patterns of these energy flux as they come out into your detectors, then you can, for example, look at some pattern and associate it back with the production of, for example, a Higgs boson or whatever particle you might like. And so what you would like to achieve is kind of a mapping between these patterns and the underlying particles. And so from an experimental perspective, the introduction of these ideas, along with kind of robust ways of actually implementing these in experiments, really reinvigorated the study of jets in QCD and really revolutionized what is possible at both particle and nuclear collider experiments. And so this has really transformed how we actually do particle physics. It has given us kind of numerous ways of, for example, searching or probing the structure of the Higgs boson, searching for new physics, understanding complicated interactions of the Quark Gluon Plasma in nuclear physics. And I could give a whole other talk on the actual kind of practical things that came out of that. But it also had a very important sociological impact, in particular for people of my generation. And it really kind of reignited, in some sense, this very or decades-old quest to actually achieve a precision theoretical description of energy flux in quantum chromodynamics. So if you just want to identify the particles which are coming out, this is kind of a yes-no question, and you don't really need a precision theoretical understanding to do this. And so there's been a lot of work in using, for example, machine learning to dig out these signals. But if you really want to ask kind of precision questions and have a precision program where you can actually kind of measure fundamental parameters of the standard model at precision level using these energy flux observables, you really need to increase the level of theoretical sophistication. And so this has really pushed people to kind of revisit this question and understand, can we really achieve a precision level understanding of energy flux in quantum chromodynamics. And so this is, as I mentioned before, very analogous to what we have in the study of the CMB. And so there we can measure these, for example, two-point functions, and we have these beautiful spectra, and we really understand it extremely precisely. And we would kind of like an analog of that for energy flux in QCD, so we can actually ask questions, precision questions, and really understand it from a first principles level. And so, of course, we are not the first people to try and ask these questions. And as I mentioned, this has a very long, in fact, 50-year-old history. And so it's interesting to just kind of look through this a little bit, since it's the kind of anniversary, and look through some of the earlier approaches, which will really inspire how we try and revisit this program. And so I should say, so I am not 50 years old. And so what I've learned about some of this earlier history has really come from talking to people that worked on this. And so if I have any kind of omissions or things that are incorrect, it's not out of my malice towards those people, but it's really just out of an ignorance or only being able to talk to specific individuals from this era. So the study of energy flux in QCD has an extremely long history, which goes or is kind of intertwined with the development of the theory of QCD itself. And so in particular, immediately after the discovery of asymptotic freedom, people realized that you could compute systematically in perturbation theory short distance quantities in QCD. And so one of the first targets, and so you can see the date, so this is really like months after the introduction of asymptotic freedom. So people realized that you could start to try and compute total cross sections, or what is another way of saying it is just two-point functions. And so they could try and compute two-point functions of currents at high injected momentum. And so this is famously done by Appelquist and George, and they computed at the one-loop order the corrections to the total cross-section, or the two-point function, and show that they were finite in QCD. And so this was a very important calculation, but of course it's in some sense antithetical to what you actually want to try and do in collider physics experiments, because the whole point of these nice pictures I showed is that you don't want just the kind of two-point function or the kind of total cross-section, but you actually want to be able to image the states which come out. So you don't want to be blind. The whole point of these detectors is you get a beautiful picture of what's happening in the actual collision. And so in particular, this was brought to the forefront with the discovery of jets, where one would like to try and understand how do you say if the energy distribution is kind of uniform. And so this is a very early collision at, say, 5 GeV, where you just get a few pions coming out. Whereas if you go to higher energies, you get these nice states which look like these jet states. And so one would like to develop a theoretical language, much like the detector experiments and these pictures which I showed, to kind of understand how to ask these questions from a first principles theoretical language. And so it's just kind of amusing to note that in this paper, they make these comments about, can one say anything about E plus E minus hadrons beyond the behavior of the total cross-section? And they said in general, the answer is no. So they also then speculated that you would not get jet events at any realistic energy, which is, of course, kind of a year or so later, proven wrong. But nevertheless, this is a kind of a very important calculation. It started people thinking along these lines. So the next important development came from George Sturman. And so this was in December 1975. So this is, again, 50 years ago, and right after the discovery of these jets. And so he was motivated by what you actually do in an experiment where you have kind of detectors, right? And so what you do with the experiment is you measure the energy flux going in some particular direction. And so he kind of suggested that you should be able to compute this, and you should be able to write down kind of operators in quantum field theory that actually replicate what you're doing in an experiment. And so what he did was to define what we would now call an energy flux operator. So it's just an operator that measures the energy going in some particular direction. And so unfortunately, he used a very unusual notation for this, where he uses eta is what should be the energy. And so what this is really measuring is the energy, or the sum of the energy of all particles going in some particular direction, exactly like what a calorimeter cell would do. And so he studied this and argued that this should be calculable in perturbation theory if you just put one of these detectors at a fixed angle on the celestial sphere. And so this was kind of the first attempt at being able to try and kind of image the states which actually propagated by introducing this kind of 3-point function, which is just the expectation value of one of these energy flow objects. And so you can really think of this as like having a modern, very fancy detector, but where you just have one individual silicon chip measuring the energy flux at some particular angle. And so in his own kind of words, at this stage, kind of energy flux became the focus of calculability because you could really perform these calculations systematically in perturbation theory. And so this was then generalized a couple years later to the study of multi-point correlation functions. So of course, if you can measure one, you can start to characterize your final state by building up multi-point functions. So this is just like in a conformal field theory, how you study endpoint functions. And so I've highlighted Stephen Ellis for a reason which I'll show in a second. But what they did was to introduce and also compute correlation functions of these energy flow operators. So in particular, they focused on a kind of so-called 2-point function where you insert 2 of these energy flow operators, and you can then look at them as a function of the angular separation between these 2 detectors on your celestial sphere. And so this is in some sense extremely analogous to what you do in the CMB, and it's kind of a very natural generalization and a very nice way of thinking about collider physics experiments. And you can see at the level of an event, you really just sum over particles and look at how they are correlated with each other. So whether the particles like to be close to each other or far away from each other. And so this is a very nice idea, and at least for someone like myself, it's very hard to kind of orient to the mindset of the times. And so he has this nice statement, which is relevant to Caltech, about the kind of rapid development of our understanding of the strong interactions at this time. And so so this was written right at the time when he introduced this, where he said the most dramatic and encouraging development in the strong interaction physics in the past few years has been the emergence of a candidate field theory to describe these interactions. And this is in sharp contrast to that 10 years ago, when at least at one well-known institution of higher learning, which is Caltech, it was taught that field theory was irrelevant to the strong interactions. And so he cites for this statement himself as recollections of a Caltech graduate student, Stephen Ellis, unpublishable. And just for reference, so he was a student here from 1966 to 1971. So this is before the kind of field theory revolution, which kind of changed our ability to compute things. And so while some of these things look very basic from a modern perspective, they were actually quite a leap at the time. And so after poking fun at Caltech, Caltech was also actually very useful in teaching a lot of people how to do these early calculations of these observables. And so in particular, the people that actually performed some of the first calculations of these were Ellis and also Stephen Wolfram. And so what they did was to actually compute these in perturbation theory, what the distribution would look like as a function of the angle. And so this was done using kind of very basic Feynman, or from a nowadays perspective, very basic Feynman diagrams. But what was quite non-trivial at the time is you were really kind of making measurements in the final state. And so from talking to Stephen Wolfram, he's kind of has very well documented all his notes. And so they actually learn how to do these integrals from Feynman. And so this is a set of notes which Feynman kind of teaching Wolfram how to actually do these energy correlator integrals. And so this really enabled people to do these integrals. And from a modern perspective, these are very nice. They're kind of some polylogs, and he did them in a nice way. But it enabled people to actually compute from first principles theories these kind of distributions of energy flux and how they're correlated. And so one of the things which is very nice about this is that because you're directly computing this correlator, you're just directly computing the final observable that experimentalists would measure. And so this was kind of the first calculation, but it really exhibits a kind of nice analytic structure analogous to scattering amplitudes, but directly at the level of the physical observable. And so they were able to actually compute this for the first time, which is very exciting. So then slightly after that, people actually went out experimentally and tried to measure these correlation functions. And so this was done in particular by this Pluto experiment shown here. So this is now, compared to the LHC, quite a small detector. But so they went and measured this at 13 GeV. And so remember, essentially what you're measuring is the correlation between energy as a function of the angle between the two detectors. So it's a function of one variable. And it kind of has two limits. One which is referred to as back-to-back, where the two detectors are 180 degrees apart. One which is referred to as collinear, where they're on top of each other, and then you kind of have an intermediate region shown here. And so what they measured was this kind of distribution shown here, which you can kind of see has some, it's a little bit of a dip, and has some enhancement in this back-to-back or collinear regions. And so this is kind of the first people that actually tried to measure this in a real experiment. And so then you can try and go and use this nice theory to actually compare with this experimental measurement. And so this was done, so it kind of pieces together a number of different calculations, all by quite well-known physicists. So this was computed in this particular limit by Parisi and collaborators. It was in this small angle limit. It was computed by Veneziano and collaborators. And then I mentioned, in this kind of middle region, it was computed by Stephen Ellis and collaborators. And so you can see that there's extremely poor agreement between the theory and the data. And so they kind of have some qualitatively similar shape, but they're kind of very far from being at a kind of precision, or claiming you could have some precision level of understanding. But nevertheless, this was kind of the beginning of a very long road towards actually trying to have a precision description of these correlations in QCD energy flux in the real world. And so over the years, kind of people measured these in many different experiments. So that was in the late 70s, and people kept measuring them in a variety of different E plus E minus experiments. So I'm not going to show them all, but just to highlight some. So this was then measured by this Mark II experiment at SLAC at 29 GeV. And you can see that the data starts to get much more smooth, but it's still extremely far from the actual theory calculation. And then in the LEP era, which I'll review in a second, it was kind of measured very nicely. So you have actually this quite precision data. And so this is actually a plot from 2017, which compares the variety of kind of state-of-the-art at that time calculations, which go from, as you go from green to red, to higher and higher orders in perturbation theory. So you can see that as you compute harder and harder and harder, you start approaching more the data, but you're still arguably quite far from the data. And you have, for example, kind of 25% errors or so. And so even with state-of-the-art computational techniques, it is extremely hard to have a precision understanding of these observables. And so in some sense, what happened is that these observables were very important for establishing QCD as the theory of the strong interactions. But then the kind of interest faded in the early 90s, and they were kind of just left abandoned. And so even so myself, when I started in physics studying jet substructure at the LHC, we weren't even aware of this kind of style of observables, and people had moved on to completely different things. And so they were essentially left completely dormant for close to 15 years. But they were resurrected in a kind of surprising context, quite far from QCD. And so in particular, they were resurrected by Hoffman and Maldacena in about 2008. as trying to come up with a simple observable which you could try and compute at strong coupling using the ADS-CFT correspondence. And so one thing which they really emphasize is that these energy correlated observables are not just an interesting observable or not just useful in QCD, but that they're really an interesting observable more generically for characterizing quantum field theories. And so in particular, they're very interesting in conformal field theories where you don't necessarily have an S matrix, but you can still study the structure of fluxes going off to infinity. And so there's this very nice picture that was made by David Simmons-Duffin. So he illustrates this with his favorite theory, which is in QCD, but it's this 2+1D Ising model. And so what was studied in these papers was a kind of simple toy experiment where you use some local operator to excite your system. So in this case, it's this hammer, which you can represent as some local operator in the CFT. You have some fluxes which come off to infinity, and then you try and measure them with some detectors, which are illustrated here by cameras. And so as you might imagine, depending on the theory, you have kind of different cameras which can exist, or different types of operators which can measure these fluxes in infinity. And so a kind of modern perspective is this, is that in addition to the kind of local operators that you might be familiar with, you actually have in each theory, associated to each theory is kind of a bunch of these detector operators which have the kind of normal or nice structures such as an operator product expansion, etc. And so there's been a lot of effort in the more formal community to understand these more general detector operators. And so this has been driven a lot by David and his collaborators. And so one thing which makes these detector operators a little bit different than a lot of the operators which you may be familiar with is that they're not local operators. But one nice thing which has come out of this is it's become possible to write this so-called energy flow operator, which I showed earlier, which was introduced by George Sturman, as an actual operator definition in the quantum field theory. And so the way that this camera operator behaves is that it's actually represented as a particular null integral of the stress tensor at asymptotic infinity. And so instead of being a local operator, what you can do is you can take the stress tensor of your theory. So you dot it into some particular unit vector, which tells you which direction you're looking at the energy flux. You then integrate it over all time, because you're imagining that your detector is just sitting there kind of absorbing the particles as they come out. And then you move this off to asymptotic infinity. And so this gives a nice operator definition of these earlier. So if you do this on free particle states, you can show that this actually gives the exact same result as these early observables of Sturman. But it's very nice in that it directly connects jet substructure with a lot of these exciting recent developments in conformal field theory. And so there was one other thing which was very important in establishing that these were really a kind of nice way of thinking about things, which was there was some calculations of the observables in a particular theory, which is a conformal field theory, but quite similar to QCD, in particular n equals 4 super Yang-Mills, where this group of people here was really showed that you could actually systematically and analytically compute these observables to higher orders in the coupling. And so this is something which had never been done before in QCD or in n equals 4 by any other techniques, and they were able to actually compute these. Again, the exact expression doesn't matter, but they were actually able to compute these to higher orders in the perturbative expansion. And so this really gave a hint that these were a kind of very nice object to try and study by themselves, and a nice way of trying to think about collider physics experiments. But what we really kind of needed was a way of bringing these back to the real world in a kind of observable that would be experimentally accessible and a kind of nice experimental signature. And so one of the things which kind of came out of this way of thinking, which is in hindsight extremely simple, but is to look for a certain scaling behavior. And so of course Euclidean scaling behavior is a kind of hallmark of quantum field theory. So for example, you can use this operator product expansion to study the scaling behavior in the energy of the two-point function, or you can use this in the study of critical phenomena. But one kind of very nice thing which came out of this study is you could actually use it to understand energy flux in colliders. And so because you have these operator representations of these detector operators, they actually admit what is referred to as a light ray OPE, or a Lorentzian operator product expansion, where you can take two of these detector operators, so for example, two of these energy flow operators here, and expand them over a basis of more general detector operators. And so the exact form of these doesn't actually matter. But the very important thing is that this predicts a scaling behavior as these detectors are brought together as a function of the angle, with some particular anomalous dimensions which you can compute systematically in perturbation theory. And so the very nice thing about this for real-world collider physics experiments is that it predicts a universal scaling behavior in the correlations in the energy flux, even in these very complicated real-world LHC experiments. And so it tells you that you can go out, or a particular thing that you could aim to understand precisely is these particular power laws in these very complicated experiments. And so this really got us motivated to try going out and actually understanding if we could do this. But there was kind of one catch. So when this was originally proposed, there's this nice exchange between Maldacena, who proposed it, and Polchinski and David Gross, where kind of when this scaling behavior was proposed as an interesting thing to look for in experiments, Polchinski said, which is a very good point, is that this huge amount of QCD data out there, why haven't people just gone out and directly looked for this? And so the response by Maldacena was, people do not do this. I've not figured out why they don't. I think they haven't thought about it. And in some sense, this was true for people at the LHC. So this kind of really got people motivated, or myself in particular, motivated to try and kind of re-attack the problem of having a precision understanding of energy flux in Collider, kind of armed with these new techniques which came from this more formal theory world. And so in particular, to try and understand how we can systematically compute and look for these nice scaling behaviors in real-world collider physics experiments. But the problem was that the LHC at that time was too hard, and so we wanted kind of a warm-up problem to first go back and do this in a much simpler setup. And so because of this, we were motivated to try and understand these energy correlator observables in the much simpler setup of LEP, which is a particular E plus E minus collider. And so the reason why LEP is extremely appealing, and in particular E plus E minus colliders, is that they really provide an exact duplication of this nice little picture that David had drawn before. And so instead of this instead of this hammer, I really have the electromagnetic current, which directly couples to QCD. And instead of this nice camera, I have this whole variety of detectors which ran in the LEP era. And so just for people that aren't familiar, so LEP was a collider which ran in the 90s, which had 4 detectors, so Opal, L3, and the 2 which I'm going to focus on more, which I've drawn their logos, were Delphi, which has this nice little dolphin, and Aleph shown up here. And so what one can ask is, can we go back and really understand these experiments very nicely from this modern perspective? And so as you may know, so these LEP experiments are really known as a legacy of extremely precise data. So both at the Z pole for precision electroweak measurements, but also for very precise measurements of this energy correlator observable. And so we were excited that we could try and go back and actually use this data and do very precise studies of these energy correlators in this very clean environment. But once we started looking into this a little bit more, we actually realized that although this data was very precise from the standards of the kind of early 1990s, from a modern perspective, it's actually not that great. And so in particular, if you try and look at the data sets which are available or extract certain parameters from them, for example, the value of the strong coupling constant, you actually get large disagreements. And so in particular, I won't go through all the plots shown up here, all the data points, but these are extractions of the value of the strong coupling constant. And so this in green is the world average driven by the lattice, and these ones over here are measurements of certain of these energy flux observables at LEP. And you can see that there's quite a large disagreement for these, what were considered as kind of state-of-the-art calculations. Also, if you actually look at the consistency of the data sets, so these are some different data sets, you can see there's actually quite large disagreements between them, particularly if you want to do actual precision physics. And so this is kind of most strongly stated here, where they kind of said that if you actually do a statistical analysis, these data sets actually don't provide any meaningful constraints on alpha S, or a way of saying this is that if you want to understand things at the kind of percent level, they actually are sufficiently inconsistent that you really can't learn much from them. And so this was a little bit upsetting, because one of the problems is that this LEP dataset has now been retired, or LEP as an experiment has now been retired. So if you go to CERN, you can actually see it. So it's just sitting here, and they have these nice posters telling you about how great LEP was. And so this is kind of a little bit demoralizing, because we currently don't have any running E plus E minus colliders. We only have these extremely complicated LHC colliders. And so what we wanted to do is to understand if one can actually go back and kind of resurrect this data and analyze it with modern techniques, and using all these nice modern theory techniques as well. And so fortunately, 2 of these experiments which is this Aleph experiment shown here, and this Delphi or Dolphin experiment shown here, actually saved all their data sets. So they did quite good data preservation for the time. And so this makes it in principle possible to actually go back, take this data and reanalyze it using modern techniques. But there's a big difference between just having some of this data on certain files and actually trying to bring it forward and do kind of percent level physics with it. But there was a faculty at MIT, Yanji Li, who in about 2017 actually undertook this as a kind of serious project to try and completely resurrect all this LEP data and make it into a modern format where you can really do kind of precision physics with it. And so fortunately, this is actually possible because even though these collider physics experiments are shut down, they have a very small number of people who are still actually active and maintaining them. And so in particular, you can go to CERN and you'll still find that there's a secretariat for this Aleph experiment. And if you go into these rooms, so there's an actual picture of a transparency of an event display. So at that time, they put event displays on transparencies, and it's actually like stuck to a kind of table in this room. And so it's actually a huge undertaking to try and go from these kind of traces of this to actually get it to data which you can analyze with nice modern techniques. And so he's had a lot of undergrads kind of studying how to extract these different things from notebooks, kind of really understanding what all these things mean. And there are a lot of kind of seemingly stupid or unexpected challenges. And so one of the things that you have to understand is that although this data was stored, it was actually just, well, it makes sense, but it was stored on kind of floppy disks at the time. And so you need to find computers that are able to actually run to be able to take this data and extract it. And so even more problematic, if you want to use kind of modern simulations of these detectors, you need to be able to extract the original models of the detectors. And so one of the problems, for example, for this Aleph detector is that these simulations of the detector are actually behind some password protection, which is still not possible to extract. So they're really on some computer, it's some old Windows computer, but it's just got a password which is locked. And so what that means is you can only use certain old simulations to do this. But for the Delphi one, you actually were able to extract all this, so it wasn't password protected, and you can actually kind of run modern detector simulations and parton shower simulations and kind of completely re-go through this. And so this has been a huge amount of effort from these experimentalists to actually go through this. And there's now really kind of a growing effort by quite a large number of people from a number of different institutions. So it's referred to as this E plus E minus alliance, and they have this nice little logo to actually use this data set for precision physics. And so one of the fun things is that compared to the LHC, where you have these kind of huge computing, the Aleph-1 data set, for example, is just 28 gigabytes. So you can really have it for like $8 on a little disk or a little thumb drive, and you can actually just do these analyses very, very fast. So with modern computing, it takes like an hour to kind of redo these analyses. And so they're extremely fun because they're just so easy to play with, and you can really just go back and get a huge amount of physics out of this data now that it's being kind of cleaned and ready for use. So what we wanted to do was to use this to go back and do a very precision measurement of these energy correlator observables. And so one objection that you might have, which is a very reasonable objection, is that just like in the CMB, these kind of correlation measurements are fundamentally limited by the detector resolution that you have. And so even though we can go back to this data, if you're just using the exact same detector, you can ask, how can we actually do better? And so just like kind of this analogy, this kind of picture of a camera which David has is kind of out of date compared to kind of modern detectors. And so one has to ask, how can one actually do better for these measurements? And so it turns out that one actually can. And so it's a little bit of a technical point, but I want to emphasize it because it is really what enabled this to go forward. And so if one remembers what I said earlier, was there was this claim that you could compute systematically in perturbation theory the flux of energy at a particular angle. But it's important that this is in perturbation theory. And so one thing you may know is that there's these theorems, for example, the Kinoshita-Lee-Nauenberg theorem, which require you to sum over all degenerate states of a particular energy. And so the problem is this is very bad from an experimental point of view, because there's a big difference in the resolution which is possible using charged particles, or tracks, as compared to just generic or neutral particles. And so in this kind of analogy, you have this kind of huge detector which really measures, for example, all the neutral particles in your hadronic calorimeter, and that's this kind of old camera, whereas inside it was actually a very, very nice tracking detector, which is an extremely, extremely high resolution camera. And so to be able to actually exploit this, we had to learn how to compute observables which are just on tracks, or just on charged particles. And so it turns out that this is actually something which is possible using kind of modern effective field theory techniques, which came out of kind of thinking about these detector operators. And so in particular, what you can imagine is that you have some detectors which are in the infrared of your theory, which really measure the actual hadrons, which is what you need if you want to talk about, for example, positive or negative charged hadrons, because that's really a property of the hadronic spectrum. You also have some UV detectors, which I kind of like zoom in and measure, for example, the actual gluons. And so what you can do is kind of a standard effective field theory technique and do some matching between these infrared detectors and these UV detectors here, which introduces some non-perturbative parameters and some renormalization group flow. But this is something which is understandable using modern effective field theory techniques, and we can actually compute extremely precisely. And so this is very important because it actually really enabled us to use these, the data just from these internal trackers, which was completely stored in this original data set, to go back and massively improve the resolution of these early measurements. And so just to kind of illustrate this in a kind of picture, this is the kind of schematic resolution that one sees in a kind of CMB map, going back to this original Pluto detector shown here in 1981, these kind of measurements by Aleph in the 1990s, and then using these kind of just this internal track-based detectors, we can really just obtain an absolutely spectacular kind of image of the energy flux with very, very high energy, or very, very high angular resolution. And so what they were able to go out and do is to then actually use this to measure these correlation functions. And so what you get out are these absolutely spectacular measurements with extremely high angular resolution of these correlation functions. I'll zoom out and go through this in a second. But in multiple experiments, so both in Delphi and Aleph, these measurements of this 2-point correlation function as a function of angle. And they actually have uncertainties on these. It's so small you can't see. And you can really see that it goes down to extremely, extremely tiny angles, both in this collinear region where the detectors go on top of each other, as well as in this back-to-back region. And so you really have just a kind of absolutely tremendous improvement in the ability to measure these observables. And so motivated by this, so if we have this huge improvement in the kind of level of the measurements, we're also motivated to kind of work very hard to actually compute these things. And so we wanted to have kind of calculations using all these modern techniques which actually match this beautiful level of precision. And so I can't go into all the details of how this is actually performed, but essentially the way that it's done is we target kind of different regions where you have some simplified kinematics, and you can perform some expansion, which allows you to compute to very, very high orders in perturbation theory. And so this can be done both in this region where the two detectors are very close together, as well as in this region where the two detectors are exactly back to back. And so they have different expansions in terms of the effective field theories, which are necessary, or the kind of techniques. But in each region, we can really compute things to extremely high precision. And so what I'll show you is the comparison between data and theory on the two different sides, and then how it combines. And so the first one we can do is this back-to-back limit shown here. And so this is a comparison, so first principles with no free parameters, of these very precise measurements of this energy flux with this theoretical calculation. As you can see that it's really kind of spectacular agreement at the kind of essentially percent level. And so to achieve this, we really had to compute these pieces or certain exponents at the for-loop level. And so this is something I did with my collaborators, but it's quite a lot of work. But it was very kind of rewarding, and that we actually got this amazing agreement at the percent level with this data. And so this was very, very nice to see. If we go to the other side, so unfortunately we haven't, oops. Sorry, I skipped it. If we go to this other side, so unfortunately here, we will hopefully soon have it also at the same level of agreement. So here I call it only good and not great. So this has been done at the kind of 3-loop level. So hopefully soon this will be extended to the 4-loop level. And so here again, you actually see this very nice scaling behavior here, which is computed at the 3-loop level from certain anomalous dimensions of operators in QCD. So again, we have extremely precise data and are actually able to compute it at the essentially percent level. And so the outcome of this was this kind of very nice evolution from these measurements in the 1980s, the 2017s, and then we're actually able to finally achieve kind of a percent level understanding of these distributions in QCD. And so there's a whole kind of very exciting program of measurements of precision QCD using this resurrected data. But instead what I want to do is to kind of use these to really push forward to the LHC and actually get to where we wanted to be of actually trying to understand these correlation functions at the LHC. And so motivated by these techniques, along with my collaborator Wajing, we really tried to push towards using these in the real LHC environment to be able to take advantage of the extremely high energy jets which are produced there. And so as I said, what we want to do is to try and target essentially the simplest possible thing one can compute, because the full collisions are extremely, extremely complicated. And so we decided to try and overcome this by focusing just on the simplest property, which is the scaling behavior as a function of the separation between these two detectors as they are brought together. Because this is kind of a universal signature, which we hoped if we could understand anything, it would be this one kind of very simple observable. And so this is actually, so first it was measured, so we motivated the experimentalist to go measure it, and this experimentalist, Meng Xiao, actually measured this inside very high energy jets at the LHC. And so what you see come out is an absolutely beautiful power law. So again, this is a separation plotted as a function of the separation between the two detectors. And if you look at the energy scale of the jets shown here, they're kind of at like 1.5 or almost 2 GeV. And you see this beautiful power law scaling over 2 orders of magnitude. And so this is very exciting to see that you actually exhibit this behavior that was predicted by Maldacena and collaborators. And so it's also very pleasing to compare this plot with the original plot by Pluto shown here. And so in doing this comparison, it's important to take into account the difference in the scales, right? So this one goes up to like 10 to the minus 1. And so this entire plot is essentially in this single data point shown here. So this is all essentially like less than 1 GeV. And so this is really showing the amazing power of these modern detectors to achieve these extremely high energies and this amazing energy resolution. And in particular, this is a plot of the citations to this original paper by Stephen Ellis. And so you can see, as I mentioned before, it kind of died off. And with these measurements, it really kind of resurrected this excitement because it really gave a kind of very nice place or a very nice interaction between theory and experiment to really try and exploit these new measurements at the LHC. And so now the challenge came to actually try and compute these. And so this is extremely complicated at the LHC as compared to an E+, E-, because the complexity of the initial state really significantly increases the complexity of the required scattering amplitudes that you need. And so in particular, to even try and compute these, you need multi-loop amplitudes of, for example, 5-point scattering. And so this is something which is right at the frontier of what is actually possible, thanks to this tremendous work by Zvi Byrne, Lance Dixon, and David Kostowers, and many else, including Cliff, who have really enabled this to even be close to possible. But when you try and actually go out and use these, so this is right at the boundary of what is possible, and you try and just out of the box use this, which was done by this group of people here, to compute these energy correlators, it's extremely computationally intensive to do this directly. And so in particular, you need to do phase space integrals over these gluons, and to make this plot, which is shown here, once you already had all the theoretical calculations to just do the numerical integrals, cost $1 million US. And with that amount of money, you only get the kind of binning which is shown here. And so in particular, all this nice scaling behavior which you wanted to see is entirely contained inside this final bin. And so using these kind of standard techniques is just not economically feasible to be able to do these calculations. And so we really needed to use these techniques, in particular this light ray operator product expansion, to be able to target these experiments, or to be able to target this behavior. And so I won't go through it in detail, but essentially what we're able to do is to kind of combine these ways of thinking coming from conformal field theory with modern effective field theory techniques to directly go after the scaling behavior. So we can essentially do this operator product expansion, reduce ourselves to some 1-point function in this very complicated LHC background, and then we just compute this at the best of our abilities. And so the very exciting thing about this is we're able to actually, for the first time, to match the precision of these E+, E- calculations at the LHC energies. And so this is something that we worked on for quite some time. So we started when these 3 students, they were all undergrads, and they're all now postdocs, so it took us a long time to actually be able to do this. But we were able to actually compute these objects at 3-loop level, the kind of scaling behavior of this. And so this kind of broke a long-standing barrier of actually being able to achieve precision jet substructure. And so you can see in these plots, you get this beautiful scaling behavior, and there's now a kind of comparison between theory and experiment. And by measuring the kind of scaling behavior of this inside these high-energy jets, we were actually able to achieve the most precise measurement of the strong coupling constant in QCD using jet substructure. And so this is the level of kind of 4% or so accuracy. And so hopefully we'll be able to extend this to what I said is what we want to be able to do is actually kind of percent level physics. And so this is kind of close, but there's a number of ways in which we can kind of improve this using a little bit more of hard work. And so we were very excited that we were able to actually achieve this and start doing real precision physics at the LHC. And so after 50 years of kind of very hard experimental and theoretical efforts, this has really transformed the study of the energy flux in collider experiments into a precision field. So we've kind of gone from this very simple plot here, where we're able to now understand at percent level and in extremely complicated collisions, the kind of behavior of these observables. And so at least from my perspective, the kind of fun in this direction is really just beginning. So this is kind of the simplest possible thing you could imagine. But it's actually now possible to measure, for example, higher point functions inside jets at the LHC. And we can use these for a bunch of very exciting things. For example, measuring the mass of the top quark, imaging higher point correlations in the Quark Gluon Plasma, and a huge variety of other things. And so there's a huge kind of potential to explore exciting physics now that we actually have these kind of tools at our disposal, and we're actually able to understand these things at the percent level in colliders for the first time. And so just to conclude, so hopefully I've convinced you that these colliders, although they've been around for a long time, they still allow us to access a number of the most exciting phenomena. And there's a lot of very exciting experimental work kind of pushing the boundaries in different directions. In the last kind of couple years, there's been this huge renewed focus on really trying to understand at the precision level the energy flux in collider physics experiments. And there's been a very nice, exciting interaction between formal theorists and all the way to experiments. And this is really kind of driving a vibrant interaction between theorists and experimentalists trying to explore and better understand the standard model. And hopefully this will continue in the years to come. So thank you.
Any questions?
This correlation function doesn't depend on what collider. It could be electrons or protons, it doesn't matter.
Very good. So if I go back, so the nice feature of this operator product expansion, sorry. So it will depend on what enters, but sorry, there's a lot of slides. But let me just, I want to. Yeah. So good. So there's an operator level operator product expansion. And so this is universal and independent of the particular state. But then what you have to do is to evaluate matrix elements of what appears on this right-hand side in the particular state. And so the nice thing about this is the leading behavior. So since you only have kind of one operator, essentially, so it's a little bit of a lie because you have an operator for quarks and gluons. But the leading behavior is always universal. And so that's what's extremely nice, and it really allows us to learn something from the E plus E minus case and apply it to the proton-proton case. So as you start incorporating more and more of these corrections, which allow you to expand about this collinear limit, then what matters is the relevant expectation value of these different operators in your state. And so these can then change the behavior of the state. And so in particular, one of the things which people are doing in, for example, nuclear physics, where you have some Quark Gluon Plasma, is you can look for how the higher twist operators in this expansion end up being enhanced in their matrix elements in those more complicated states. And so the thing which carries the state dependence is really the expectation values of these different operators and their kind of relative sizes.
You're able to extract those coefficients in terms of visit rates. Maybe you can probe the structure of protons.
Yes, absolutely, absolutely, absolutely. And so there's a large, so I didn't go into it as much, but there's a very large industry, in particular now from the nuclear physics community, of measuring these in deep inelastic scattering experiments. So you can now measure energy correlation functions in those, to try and understand the structure of the proton. And so there's now a huge kind of industry of trying to do this. And so I didn't show them, but people have also, so there's this collider called HERA, which is a deep inelastic scattering experiment, and it also has archival data. And so people have gone back and they've actually measured this also in that scattering experiment, exactly with the perspective of trying to understand essentially the expectation value of these objects in like proton-like states. And then you can really use this to characterize the proton. And so these detectors, so one thing which I didn't mention, but which was suppressed in these, is that these operators appearing in here can also carry certain spin indices or kind of polarization information. And so this is something which is also very interesting from the nuclear physics perspective. And so people are trying to use this to constrain the behavior of the proton. Absolutely, yes.
So actually, I had a question.
Sure.
I guess rather famously, there's a lot of models beyond the standard model that have missing energy as a signature. Is there any sense in which like energy correlators would be more sensitive to something with missing energy? And maybe even more broadly, is there some kind of target coupling or observable that for which you think this would be like better than any other method?
Yeah, good. So for beyond the standard model, yeah. So I think one thing which will be ultimately very useful, it has not been kind of thought about in this, or it has not been like processed in this language, but is these measurements of the scaling behavior, right? What they're really probing is the like anomalous dimension as a function of the scale, and the scale that's actually being probed is like the energy of the jet times theta. And so in this one single measurement, you're sweeping through from like the TeV scale to like essentially a GeV, where you get confinement. And so you're really measuring the detailed structure of anything that lies in there. And so if you add anything that corrects the anomalous dimensions, even at like a virtual level, it will lead to kind of a little kink in these distributions. And so I think this is so there's a huge amount of physics in these plots, particularly as you get them to the percent level. And I think it should be reprocessed in that language. And this puts very strong constraints on anything below this particular scale, even if it appears just virtually. So this is something that was done using kind of very old data by Kaplan and Matt Schwartz, but it could be done in a very, like these are now infinitely better measurements and should be reprocessed in that language. And it's something that people haven't gotten to, but I think they really measure things across a very wide range of scales and would be interesting to do in that. I think it'd be complementary, yeah. Because one of the differences, so a lot of these searches for new physics are based on kind of tagging or looking at things at an event by event level. The difference with these is you only get out some kind of statistical ensemble. And so it's more like how people look for things in the CMB as opposed to in at the LHC. But I think as you really move towards like precision or very small effects, this is probably the way to actually do it. And so I think this is something that so these measurements are only in the last kind of year or so to show that this is possible at Hadron Colliders. And I think then people will try and do physics with it. It also, by having, so as compared to many other observables, because you actually keep the full angular information, you really get access to like spin polarization effects. And so this also encodes, let's say like higher dimensional operators, anything that measures this in a very, very sensitive way. And so I think people just haven't quite gotten to that level of that yet, but I think they do in a very nice way. Yeah.
Now let's thank Ian again for that.